Hello students. So this begins, if you like, something like the second half of the course content-wise, although this class had a fairly jarring delay at what you might consider the middle. So what we're going to do for the rest of the class is we're going to study trigonometry and the trigonometric functions. So it'll all be focused around two functions, one called sine theta, one called cosine theta. And here's a description. So here's how you describe the trigonometric functions. Look at a circle. Start at the point 1, 0 on the circle of radius 1, centered at 0. So this point right here is 0, 0. Pick some angle, theta. So that theta is some number. If it's measured in degrees, maybe it's like 45 degrees, maybe it's measured in radians, so it's like pi over 4 radians. We'll talk about radians and degrees today. Rotate by that angle. So there's this angle theta you want to rotate by. Start there, rotate around by this angle of theta. You'll land at some point. You're at some point x, comma, y. Cosine of theta is the x-coordinate of the end location. So this x value is the cosine of theta. The y value is sine theta. Sine theta is the y-coordinate, so that y is the sine of theta. So there's an overview of what the trig functions are, and we'll study them a lot for the rest of the semester. Before I can talk about those trig functions, I need to talk about this. What the heck does an angle of theta mean? How do you make sense of that? So today what will we do? We'll measure angles. So let's try to figure out what angle measure is, and let's start with something that maybe you'll find more familiar, though somehow it has less reason for this notion of angle measure to be used. So when someone says an angle of 1 degree, what do they mean? Well, let's just think about degrees. 1 full revolution, maybe you just know, amounts to 360 degrees. So to understand degree measure of an angle, you take a full revolution, you break it up into 360 equally sized pieces. So 1 degree gives 1/360th of a full revolution. So that's all it is. If you want an angle of 5 degrees, it's 5/360ths of a full revolution, and you can simplify that. 90 degrees will be 90/360ths of a full revolution. But let's simplify that. (90/360), well, let's see, those zeros cancel. 36 is 9 times 4. So this will be 1/4 of a full revolution. So if you want to draw a 90-degree angle, you want 1/4 of a full revolution. So all the way around would be 1 full revolution. I want 1/4 of that. This is 1/4 of a full revolution. So this angle is a 90-degree angle. And that agrees with what you remember, right? 90 degrees should be like a right turn. So here's my objection, though. There's no natural reason to break the circle into 360 pieces. We do it because the Babylonians did it. The Babylonians did it because their number system treated the number 6 as a special number. Same way as we think of 10 as being a special number. We walked base 10, they walked approximately base 6. So 36 was a natural number for them to use. There's nothing special about it, though. So what we're going to do is we're going to introduce a way of measuring angles which doesn't involve this arbitrary choice of how many pieces you want to break a circle up into. We will use a radian measure, which will be geometrically meaningful. And one of the important things about radian measure, which won't come up in this class, but will in things like calculus, is things like calculus works very well if you do it over a radian measure. It doesn't work so well if you do it over a degree measure. But let's start in on what radian measure means. Definition. If you stand on a circle of radius r, so let's draw a picture. There's a circle, a perfectly drawn circle. So it turns out my penmanship on a tablet is even worse than on the board. Let's suppose that has radius r. So the r is the radius of the circle. Start at a point on the edge of the circle and walk counterclockwise, say that far, some length s. So r is in some units of distance, s is in some units of distance. That's fine. Well, check it out. You've just traced out an angle. That in there is an angle. The radian measure of that angle is exactly s divided by r radians. So this angle of s divided by r radians. So let's just go ahead and walk out some examples. So let's suppose that you start on a circle of radius equal to 2. You draw an arc length of 2 centimeters. What is the radian measure of that? Well, the radian measure, I'll often use theta for my angles. So the radian measure of this angle, theta, is the arc length divided by the radius. That is 2 centimeters divided by 2 centimeters. The centimeters will cancel. Equals 1 radian. So you'll notice that right here the units on those distances just canceled. So in some sense this is a unitless measure. It's just 1. But the fact that it's 1 radian tells you that that 1 is the ratio of radius to arc length. Similarly, let's think about this one. So here is a circle with arc length 6 drawn on a circle of radius 1.5. So this has some angle measure. Switch color. Yeah, no, let's stay the same. So there's the angle, theta. Theta is equal to s over r when measured in radians. S is 6. S is the arc length divided by the radius, which is 1.5. So this is 6 divided by 1.5. I guess that's the same as 60 divided by 15 because that's how division works when decimals are involved. That's exactly 4. Cool. So there's how you measure, find the radian measure of an angle. You just compute the arc length, you compute the radius, you take the ratio. And here's the thing to notice. There was no arbitrary choice here. The ratio of arc length to radius, those are both things that you should be interested in if you're doing geometry, is, if you like, a natural choice. There's nothing arbitrary. Which is what my objection was about degrees. So radian measure is a natural measure of an angle. Maybe here's another natural measure of an angle. Full revolutions. You can just say, well, how much of a full revolution does this angle trace out? It does 4/5 of a full revolution? Great. That's a perfectly reasonable way to measure an angle. Let's try to translate between them. So And let's start by computing the angle corresponding to one follow evolution. So I'm going to try to have both of these in screen. Let's stand on a circle of radius r. So the radius of this circle is r. Let's start at the point, at that point on the circle. It doesn't matter which point you start with, where you start. Let's walk counterclockwise all the way around the circle. That traces out some angle. It traces out an angle equal to one follow evolution. What's its arc length, though? Well, to compute the arc length, maybe you need to remember one thing. This s is equal to, well, I guess it's the circumference. And no one's here to correct my spelling, so I just double-checked. That is how you spell circumference. I really wanted to replace that f with a ph, but no, that's correct. Is the circumference of a circle, which maybe you remember is given by the formula 2 pi times the radius of the circle. So this arc length that you've just traced is the same as the circumference of a circle. It's 2 pi times the radius. S is equal to 2 pi r. And the reason that you need to compute that is I want to know the angle measure of this follow evolution. I want to know how big is that angle. Well, the radian measure of that angle is the ratio of arc length to radius. So let's just write that down. This covers an angle of s equal to 2 pi r divided by a radius of r. Well, that's just 2 pi radians. So this angle right here, this color, is 2 pi. Good. So what's the conclusion? One follow evolution in radian measure is 2 pi radians. Nice. So that tells us lots of information. So let's use this fact to convert between degrees and radians. So in order to make this conversion, well, I need to know some relationship between radians and degrees that'll let me convert. Well, I know one thing. I can express one follow evolution now in terms of both radians and degrees. We just found that one follow evolution is 2 pi radians, but one follow evolution is also 360 degrees. So that means if you want to convert from radians to degrees, you can do so by just multiplying by 1 in a creative way. So I'm going to multiply by 1 twice in a way that cancels units. And this is the standard way to convert units. So d degrees is the same as 1 revolution divided by 360 degrees. All right, because 1 revolution is equal to 360 degrees. So all of this is secretly just equal to 1. And you'll see immediately, it looks like the degrees now cancel, and now you're in units of revolutions. So I want to cancel the revolutions and wind up with radians. Well, 1 revolution is the same thing as 2 pi radians. And now you see revolutions divided by revolutions, so those will cancel. And so now the only units left are radians, which is what we wanted. We wanted to convert from degrees to radians. Let's just write out what we have. We see d multiplied by, in the numerator I see 2 pi, in the denominator I see 360. Let's make that 2 pi less terrible looking. So to convert from radians to degrees, you just need to multiply by 2 pi over 360. And that's correct, but whenever you get a formula, if you want to actually use it, which we will, an awful lot, you have to simplify. I see a 2 in the numerator, and the denominator is even. So I can divide the denominator by 2 and cancel the 2 in the numerator. So d times pi over 180. So d degrees is exactly the same as d multiplied by pi over 180 radians. So if you want to convert from degrees to radians, multiply by pi and divide by 180. Going the other way, well, you should have to do the opposite of multiplying by pi over 180, so I guess that should be the same as multiplying by 180 and then dividing by pi. But let's just check that. If you start with an angle of theta radians and you want to convert it to degrees, well, first, get rid of the radians and get revolutions into play. 1 revolution is the same thing as 2 pi radians. So if we multiply by this quantity, which is again just 1, the radians will cancel, and I'll wind up with revolutions. I want to wind up with degrees, though. So I'll multiply again by 1 in a creative way. 1 revolution is the same as 360 degrees. The revolutions now cancel. And what are we left with? We're left with theta times 360 over 2 pi degrees, because the only units left were degrees, right? Oh, theta, not 0. That's the same thing as theta multiplied by 180 over pi. So an angle of theta radians is the same as an angle of theta times 180 over pi degrees. So let's just do some examples. Let's suppose you want the radian measure of a 30-degree angle. Well, to convert from degrees to radians, it looks like d degrees is the same thing as d times pi over 180 radians. So 30 degrees will be the same thing as 30 multiplied by pi over 180 radians. And simplifying, I see that the numerator and denominator are both multiples of 10. So I can cancel that. 18 happens to be 3 times 6. So this will simplify further to pi over 6 radians. Determine the degree measure of an angle of pi over 5 radians. Well, to convert from radians to degrees, multiply by 180 over pi. So pi over 5, that's the number of degrees I want. I need to multiply it by 180 over pi. The pi's cancel, and you wind up with just 180 divided by 5. So, right, the tricky way to divide by 5 is it's easier to divide by 10, so let's just multiply and divide by 2 and then divide by 10. So multiply 18 by 2, you get 36, so 18 times 2 is 360 divided by 10. That's 36 degrees. All right, so last things last. If you recall, there is a right angle, which measures 90 degrees. Let's convert that to radians. So 90 degrees is the same thing as 90 times pi over 180 radians. Well, 180 is exactly double 90, so that just leaves us with pi over 2 radians. So a right angle is the same thing as pi over 2 radians. Very good. So what we've done so far is measuring angles. I think I'm going to go ahead and split this recording into 2 using this as the splitting point, because the next thing that we're going to do is we're going to start doing some geometry with this information. So we have a very natural way. If I tell you the radian measure of an angle, then I've basically told you the arc length you get when you trace it out. What we'll do in the next video is we'll extend that to things like area of a sector. And beyond area of a sector, we'll talk about the speed at which a spinning thing spins and the different ways you can measure that. Nice. So I'll go ahead and stop here.